Before the ARPANET, telecommunications relied entirely on circuit switching, reserving a dedicated, continuous copper path for a single conversation. The ARPANET bypassed this physical bottleneck by introducing packet switching. It chopped data into discrete blocks, dynamically routing them through a shared web of cables. To manage the flow of these packets across the host computers, engineers developed the Network Control Program, or NCP. This protocol acted as the first set of traffic laws for the early Internet, allowing machines to establish connections and transfer files. But NCP had a strict architectural dependency. It worked only because the environment it operated in was perfectly uniform. Looking at these early mainframe rooms, you see a sprawling, identical physical infrastructure. NCP relied entirely on this homogeneity, standardized mainframes connected by reliable terrestrial copper wires with predictable signal degradation. The constraints of this design became apparent when researchers attempted to push the network's physical boundaries. In the mid-1970s, the Defense Advanced Research Projects Agency wanted to connect mobile troops in the field and ships at sea, requiring data transmission over volatile radio waves and satellite links. A protocol engineered for the predictable environment of wireline copper could not handle this new complexity. When introduced to the chaotic variables of the outside world, the ARPANET's foundational logic began to fail. Engineers introduced two new experimental systems, the Mobile Packet Radio Network, or PRENT, and the Orbital Atlantic Packet Satellite Network, known as SATNET. These mediums operated on entirely different physics than the original wireline ARPANET. Radio transmissions are inherently noisy, suffering from atmospheric interference and high packet loss as signals bounce off terrain. Satellite networks, beaming signals thousands of miles into orbit and back, introduce massive propagation delay, or latency. NCP lacked the mechanisms to bridge these environments. As this matrix illustrates, when data attempts to cross from a stable terrestrial wire to a volatile radio or satellite link, the packets simply disintegrate. The protocol could not account for the dropped packets of radio or the massive delays of space, causing connections to instantly time out at the network borders. This collision of mediums birthed a new engineering objective, building a CatNet, short for a concatenated network. The goal was to stitch these physically incompatible infrastructures together into a single functional system. The central engineering tension of the 1970s was now clear. Researchers had to figure out how to guarantee mathematically reliable communication across a CatNet built from physically unreliable and wildly varied components. In 1974, computer scientists Vint Cerf and Bob Kahn published a blueprint to solve the heterogeneity problem. They proposed a universal standard called the Transmission Control Program. Their initial design was monolithic. This schematic shows the original TCP header tightly encapsulating its data payload. Within this single layer, the protocol handled two entirely different tasks: physical routing from node to node and sequence checking to ensure reliable delivery. Combining these functions created an immediate operational bottleneck. By bundling routing and reliability together, the protocol forced every single network to adhere to the exact same strict error checking rules, regardless of its physical medium. Because a high-latency satellite link takes far longer to acknowledge a received packet, the fast terrestrial networks were forced to wait. The entire system throttled its speed down to match the slowest connection, devastating overall throughput. When network intelligence is centralized in a single, rigid protocol layer, it creates an inflexible bottleneck. The monolith could connect diverse networks, but it could never scale efficiently. The limits of this design were proven on November 22, 1977. Engineers executed the three-network demonstration, setting up the ultimate real-world stress test for cross-medium routing. This map traces the test packet's journey. Originating in a California van via packet radio, it routed into the ARPANET, beamed to an Atlantic satellite, and returned to USC. Maintaining this continuous stream across these diverse mediums was a massive logistical feat. The test yielded a dual outcome. It successfully proved that diverse, heterogeneous networks could be chained together into a unified system. But it also definitively proved that the monolithic TCP header was far too rigid to handle global traffic at scale. To save their concept of a network of networks, the architects realized they had to decouple the operations. They needed to separate the act of moving the data from the act of verifying the data. Engineers cleaved the monolithic protocol in half. The dumb, stateless Internet protocol exists solely to forward packets at blistering speeds. Conversely, the smart transmission control protocol operates exclusively at the edges, using sequence numbers to ensure data is perfectly reassembled. This separation codified the end-to-end principle, formally articulated by computer scientists Salzer, Reed, and Clark. Unlike traditional telecommunications, which placed all processing power inside the centralized network switches, the new Internet model pushed the intelligence out to the host computers at the outer edges. This architecture established the concept of fate sharing. Look at this multi-node network path. If a core router suddenly goes offline, the connection survives and dynamically routes around the damage. The state of the transmission is held only by the smart endpoints, not the dumb core. By stripping intelligence from the network core, the system became infinitely resilient to localized physical destruction. The infrastructure could fail, but the endpoints automatically recover. This theoretical architecture became historical reality on January 1, 1983, a deadline known as Flag Day. On this date, the ARPANET permanently decommissioned the old network control program and mandated that every connected host switch to the new TCP IP stack. The transition yielded an immediate operational payoff. With the flexible TCP IP framework in place, the network could finally be physically split to isolate sensitive military communications from civilian academic research, without losing the ability to route between them. The simple infrastructure was bifurcated. As you see here, the massive cluster of nodes separated into two distinct spheres. The civilian ARPANET and the classified MILNET were now structurally independent, orchestrated by exterior gateway protocols that maintained a highly controlled, secure link between them. Flag Day marked the precise moment the experimental network completed its metamorphosis. By decoupling the protocol from the physical wire, it officially became the modern Internet. The legacy of this architectural split is best understood through the hourglass model. At the wide base, you have an ever-changing array of physical layers: Ethernet, Wi-Fi, optical fiber, and 5G. These all narrow into a single tiny waist, the Internet protocol. Expanding back out at the top is a vast array of software applications. The engineering brilliance of this model lies in that narrow waist. Because the IP layer is strictly standardized and entirely stateless, any physical network hardware built below it can transmit data, and any software application built above it can receive that data. They never need to interact directly. This creates a dynamic known as permissionless innovation. The core IP layer never has to be rewritten to understand new applications. Developers at the edges were completely free to invent the World Wide Web, streaming video, and modern encryption, while the center waist remained totally unchanged. The Internet did not conquer the globe by engineering the smartest, most complex centralized infrastructure possible. It succeeded by doing the exact opposite. It embraced strict modularity, stripped all intelligence from the core, and pushed the raw power of computing out to the absolute edges.